The geology of the Earth's climate, past, present and future. A narrated PowerPoint show presentation. The geology of the atmosphere. The atmosphere is the outer layer of the Earth where the gaseous components largely reside and is where all the Earth's weather occurs. The distribution of nitrogen, oxygen and carbon dioxide in the Earth's atmosphere, derived originally from volcanic gases at the time the Earth formed, have been affected by interactions with the oceans, each other, the solid Earth and living organisms, and has changed dramatically over time from an original atmosphere the same as present-day Venus, with 98% carbon dioxide content. Where did all the Earth's original 98% atmospheric carbon dioxide go? It went into the oceans to form limestones, calcium carbonates, which is 44 weight% carbon dioxide. The mean global temperature of the Earth is a warm 15 degrees centigrade. Without these blanketing, insulating gases, the global Earth temperature would be considerably lower overall, with hot days and very cold nights, with a mean surface temperature of minus 18 degrees centigrade. The sun heats the Earth and oceans, which in turn heat the atmosphere and circulate that heat largely by convection. Examine the three illustrations at the bottom of this slide for some more relationships relevant to this early and present-day atmosphere. Greenhouse gases. A greenhouse gas is a gas that absorbs and emits radiant heat within the thermal infrared energy spectrum, causing the warming known as the greenhouse effect. The primary greenhouse gases in the Earth's atmosphere are water vapour, gaseous water, up to 4% of the atmosphere, carbon dioxide, methane, nitrous oxide, and a couple of others. The water in clouds is not water vapour, gaseous water, but liquid water droplets. The heat amplifying effect of water vapour is enough to significantly increase the warming caused by carbon dioxide in the atmosphere. Water vapour accounts for about 50% of greenhouse gas heating. Clouds, through trapped heat, another 25%, carbon dioxide 20%, and the remainder about 5%. Water vapour, this does not include water droplets as in clouds, is a powerful greenhouse gas comprising about 95% of the greenhouse gas inventory and is by far the dominant influence, but does not contribute to what is called the enhanced greenhouse effect because it is not increasing in abundance. Greenhouse gases absorb light, causing the bonds between atoms to vibrate, trapping some of that energy, preventing it from escaping back into space, and in the process further heating the atmosphere. The difference between climate and weather. Weather is the short-term atmospheric condition over a localized region and over a relatively short time frame. It is not an average and can vary quite markedly over short periods. Climate is the regular characteristic pattern, including seasonal variations, of the atmospheric conditions for a large region, which tend to be repeated annually over a long period. Climate change occurs if the climate, as described above, changes noticeably and consistently over time. Geologists can determine and quantify past climate conditions by using many geological markers and features that they can see in the rocks and the landscape, sometimes referred to as climate proxies or surrogates.
that indicate that particular climatic conditions existed at the time of rock formation. The Earth's climate has not been constant, but has changed, sometimes dramatically over geological time, but has remained within manageable limits for nearly all life forms for most of the last 4 billion years. Climate markers, sometimes referred to as surrogates or proxies. 1. Glacial gravels, called moraines, and glacial outwash gravel plains, referred to as tillites, extensive scoured rock pavements, U-shaped valleys, ragged pyramid-shaped rocky mountains, all indicate major ice events and periods of glaciation in the past. Thick coal accumulations indicate temperate and tropical climatic conditions. Coral reefs and shallow marine limestones also indicate tropical conditions. Deserts, desert landforms, salt lakes, evaporites, calcretes and calcareous carbonate-rich soils indicate hot arid conditions. Many surface landscapes and soil varieties are climate specific. Evidence of former higher sea levels, illustrated by emergent reefs, raised beaches and shorelines, exposed marine rock units, accompany glaciation episodes as sea level is lowered locally as extensive ice builds up on land globally. Evidence of former lower sea levels provided by present-day drowned coastlines and drowned former valleys such as Sydney Harbour. The most important proxies are the fossil record of flora and faunal distributions of climate-sensitive species commonly reflect specific climate conditions. Oxygen isotopes, oxygen 18:16 ratio studies, give us a numerical value for past temperatures. The ratio sourced from a range of materials is directly linked to water temperature of ancient oceans and ancient climates at the time that these ratios and the host rocks were formed. Earth climate over geological time. This chart displays the departures from the mean global temperature and mean global precipitation over the last 4 billion years, determined from geological climate markers over that period on Earth recorded from the rock record. The medial lines for temperature and precipitation on these charts represent the present day values extended back in time as a line of reference. Departure from the medial lines reflect the magnitude of the change. The maximum temperature above the medial line ranges from 5 to 7 degrees centigrade. The blue dashed line in the global temperature chart represents the long-term mean temperature condition established over the 4 billion year period, which is some 3 to 5 degrees warmer than at present. For most of Earth history, conditions have been 3 to 5 degrees warmer than at present, sometimes warmer and wetter and sometimes warmer and drier, but for more than 95% of all time, conditions were warmer, and throughout most of that time there were no polar ice caps. A point to notice on the charts along the left-hand margin is that the age or time axis is not of constant scale. Portions have been compressed or extended to highlight important features in that interval. Here is another very much more detailed chart of mean global temperatures as departures from the present day mean global temperature line.
We can see that the long-term global temperature of the Earth has been remarkably constant, as represented by the dashed red line slicing through the orange-shaded peaks in the top chart. This suggests that the mean global temperature for most of Earth history has been up to 3 degrees warmer than the present-day mean global temperature. The lower chart represents the last 1.8 million years, only 0.04% of all time, and has been greatly expanded and shows the warmer peaks in the more recent time to be of the same magnitude as to where warming is heading today, but did not cause massive climate disruption, extinction of the polar bears, and other life forms.
The Earth-Sun thermal equilibrium. The Earth's temperature and other related climate factors are totally controlled by an incredibly stable dynamic thermal equilibrium that exists between the Sun and the Earth. The Earth's temperature has remained remarkably constant at some 3 degrees warmer than today for several billion years and is slowly re-equilibrating to this long-term warmer temperature norm following the last glacial event. The relationships are displayed in this diagram. Provided this relationship remains relatively constant, the Earth's climate should not vary significantly and should maintain a constant thermal equilibrium and mean global temperature. The Earth's tilt axis causes seasonal variations. Ice ages occur if the radius of the orbital ellipse increases and warming if it decreases. Here we have a chart of past atmospheric carbon dioxide concentration proxy measurements, alongside proxy temperature measurements, displaying considerable divergence between the two over geological time. Various proxy measurements have been used to determine atmospheric carbon dioxide concentrations millions of years in the past. These include boron and carbon isotope ratios in certain types of marine sediments and the number of stoma, air holes, observed in fossil plant leaves. Phytane, a breakdown product of chlorophyll, is now also used to estimate ancient CO2 levels and gives a continuous record of carbon dioxide concentrations. In this temperature versus time chart, we have displayed temperature, the red curve, and atmospheric CO2 levels across the time range as the blue curve. We can see that the blue curve representing carbon dioxide levels is not consistent with variations in the temperature levels in the red curve. In the left-hand side of the diagram, where we have the highest carbon dioxide levels, we also have one of the coldest periods in Earth history, a major glaciation. In other parts of the chart, we have carbon dioxide and temperature coincidingly low in the Carboniferous Permian period. Overall, we see no consistent relationship between parts per million carbon dioxide in the atmosphere and the prevailing mean global temperature for the Earth during these same periods.
Another more striking feature of the atmospheric carbon dioxide data in the blue curve is the consistent progressive decrease in CO2 over time from over 2000 ppm in the Precambrian to around 300 ppm in the 1700s. During this dramatic decrease, the Earth's mean global temperature remained consistently some 3 degrees warmer than today, as atmospheric CO2 was virtually eliminated from the atmosphere. During most of this period, there was virtually no consistent correlation between carbon dioxide and temperature. Outside glaciation episodes, mean global temperatures remained consistently around 20 degrees centigrade as atmospheric CO2 decreased by 85%.
The carbon dioxide debate. Carbon dioxide is the most oxidized form of carbon, forming a stable, relatively inert gas in the atmosphere, currently just over 400 parts per million. Bicarbonate is the stable form dissolved in water, which contains 60 times more abundant carbon dioxide than does the atmosphere. Carbonates are the stable solid form, mainly as calcite, calcium carbonate, or limestones. Limestones are 44% carbon dioxide by weight and form a major rock type, often entire mountain ranges. More than 99% of all the carbon dioxide component formerly in the Earth's early atmosphere is now locked up in carbonate rock. Atmospheric carbon dioxide. Certain trace gases in the atmosphere are thought to maintain the Earth's temperature at a fairly constant level. These gases are called greenhouse gases and have the effect of preventing incoming visible radiation escaping as infrared radiation. The trapped radiation wavelengths heat up the atmosphere at the surface, but only to a limited extent, dropping off dramatically as their abundance increases. The main greenhouse gases and their thermal influences are presented in the table below.
Here is a table of the relative heat retention capabilities of carbon dioxide and methane. Also presented is a table of pre-industrial revolution and modern levels of these two main greenhouse gases of concern. Human activity, burning fossil fuels and burning biomass, has caused much of the increase in carbon dioxide. Volcanic gases can also, but very irregularly, produce large amounts of carbon dioxide. Burning all the fossil fuels in existence would produce an atmospheric level of CO2 of around 2,000 parts per million. To halve the present carbon dioxide level from 400 parts per million to 200 parts per million would probably annihilate all terrestrial vegetation, already starved of adequate carbon dioxide, and dependent animal life on Earth. Therefore, decreasing atmospheric carbon dioxide would be a far greater concern than increasing it. Methane is sourced through rice cultivation, ruminating animals, coal mining, natural gas venting, and incomplete biomass oxidation.
Carbon dioxide, the molecule of life. The single most important molecule, in fact the building block for all life, is carbon dioxide, CO2. Carbon dioxide is the only molecule on Earth that absolutely all life depends on, even more so than oxygen, which itself is derived entirely indirectly from carbon dioxide. Carbon dioxide is responsible for every carbon atom and every living thing that has or will ever be, every molecule of atmospheric oxygen that has ever existed, all the food that supports all life through its essential role in photosynthesis, for nearly all non-solar, non-nuclear energy in existence through fossil fuels. Ice core temperature and carbon dioxide data over time. Carbon dioxide is measured directly in trapped air bubbles in ice cores. Temperature, however, is inferred from the isotopic composition of the water molecules released by melting the ice cores. Based on the analysis of entrapped air and water from ice cores extracted from permanent glaciers from various regions around the globe, it has been demonstrated that the present cycle of global warming began 18,000 years ago, accompanied by a steady rise in atmospheric carbon dioxide. The correlation of carbon dioxide with temperature appears clearly demonstrated, but correlation does not always mean causation. Negative correlations between temperatures and carbon dioxide levels, the red shading in the adjacent diagram, should not happen if there is a consistent correlation indicating causation.
From evidence already presented, it appears that there is no consistent relationship between atmospheric CO2 and global warming temperatures. And also, there's no relationship between the highly variable atmospheric CO2 levels and the near constant global mean temperatures over all of climate history. This then means that atmospheric CO2 cannot be involved in warming and is therefore not a polluting exhaust gas from fossil fuel burning. But what about CO2's known greenhouse effect on temperature? The crucial point is that CO2 does not significantly contribute to global warming if it is already above about 200 parts per million. The bar chart on the right shows that temperature effect of increasing increments of 20 parts per million CO2 added to the atmosphere. The first 20 ppm creates a temperature increase of about 1.5 degrees centigrade. The next 20 ppm just adds on 0.3 degrees centigrade. And as you add successive increments of 20 ppm CO2, the temperature effect further decreases down to about 0.02 degrees centigrade per 20 ppm additional CO2. Here is another variation of the atmospheric carbon dioxide decline, this time over the last 140 million years. The decline is linear and achieving very low levels of CO2. In the circle in the lower right part of the chart, CO2 can be seen to approaching the survival threshold for vegetation. The brown shaded area shows the range of vegetation CO2 starvation in this system. Recent man-made increases in atmospheric carbon dioxide has had a recognisably positive impact on global vegetation. See the next slide. This means that we don't have to unnecessarily remove and sequester harmless CO2 exhaust gases at huge cost. Carbon dioxide is not a problem and can be allowed to escape into the atmosphere as a beneficial gas where it is effectively dealt with in the wider environment, absorbed into the oceans, or generating new life as very productive fertilizer. This means that clean coal already exists without needing to remove the carbon dioxide. The effect of increasing levels of atmospheric CO2 on plant growth is illustrated in these photographs. The numbers are additional carbon dioxide above ambient levels, 385 ppm in the initial state, and total atmospheric CO2, which includes added CO2. Horticulturalists regularly increase CO2 levels in glasshouses to artificially promote optimum growth and achieve these benefits. Atmospheric CO2 is an essential plant fertilizer delivered free daily to every plant on Earth and is not a toxin. At levels below 200 ppm carbon dioxide, plant growth virtually ceases. In the last 35 years or so, with the advances in satellites scanning the Earth's surface, we've been able to put together changes in the Earth's vegetation seen over that period of time. So what we have seen since about 1982 up until about 2015 is a significant increase in the greening or the vegetation cover of the Earth, as represented in this diagram. This is a percentage increase of leaf area determined from satellite imagery. Every colour that is green or higher coloured greens represents an increase in this percentage leaf area of vegetation throughout the world. Those colours that are not green, to the left of the zero position, which is yellow, to the reds and purples, where there is a decline in the vegetation cover. It can be seen that in many places there's a very dramatic increase in vegetation of the order of 25% or so over large portions of the Earth's surface. This is due solely to the man-made contribution of CO2 to the atmosphere.
Carbon dioxide, limestones and coral reefs. Atmospheric carbon dioxide is continually recycled by terrestrial plant life through the processes of photosynthesis, animal life, the Earth's ocean in the form of bicarbonate iron, and eventually into calcite in the form of limestones, coral reefs, animal shells and skeletons, and carbon energy reservoirs of coal, petroleum and gas. The oceans contain more than 60 times as much carbon dioxide as the atmosphere and are in equilibrium with marine limestone deposits. Limestones and coral reefs require carbon dioxide-rich environments to form, which in turn favour shallow, warm water, low latitude, nearshore environments. High carbon dioxide levels in fact favour the production of coral reefs. Most of the world's carbon dioxide is in limestone, 44 weight% carbon dioxide, and they make up a considerable proportion of surface and subsurface rock sequences, including all the world's coral reefs and entire mountain ranges in many parts of the world. Nearly everything you see in the photos below, including the hills, coral reefs and mountains, is composed 44% of carbon dioxide. Atmospheric CO2 and major events in the evolution of life over the last 500 million years, including the ascent of man and mankind's cultural evolution. This chart shows major developments in the evolution of life plotted against a declining atmospheric CO2 content and time. We can see the massive decline in atmospheric CO2 accompanying the explosive development of the first land plants about 400 million years ago. As evolution progressed, increasingly diversified life flourished, eventually progressing to the ascent of man, with modern man only appearing in the last 1 million years or so. We can see the CO2 relationship of all these evolutionary developments, but also in relation to mankind's cultural evolution. In particular, there seems to have been no effect of CO2 levels on man's cultural development or cultural evolution. Many climate alarmists recognise earlier climate highs going back in geological time, some millions of years, predating human existence and evolution, and are concerned that future heating events may make life unbearable for modern humans who have never experienced these earlier conditions. This chart shows the last 1 million years of climate history, extending back to the development of our early human-like precursors.
It appears as though mankind and precursor forms managed very successfully for 4 previous recent warming episodes, and that a new cooling cycle is imminent. Here is a chart of Greenland's ice sheet surface temperatures over the last 4,000 years. Looking back over the last 4,000 years of climate history and covering humanity's most recent cultural history, again shows that global temperatures significantly warmer than today in the past offered no impediment to human cultural development and progress, and is unlikely to do so in the future. Of note is the warming and cooling rates of about 1 degree per 100 years for the major warming and cooling episodes. The Earth's climate can change dramatically and very quickly over time for geological short periods on occasions. Here we have a reconstruction of how New York as it would have looked during the last ice advance 18,000 years ago. In the top left of the slide we see the thickness of ice sheets 21,000 years ago superimposed over the skylines of Toronto, Chicago, Boston and Montreal. We can see from these depictions that ice sheets of the order of well over 1 kilometre were not uncommon in North America. Greenland ice cores. The interesting features of these charts is the regularity of the warming episodes. Every 1,000 years, each lasting 200 to 300 years, with around 2 to 3 degrees temperature shift up and down, with warming and cooling rates of around 1 degree per 100 years, the same rate is presently estimated for the current warming. There is no correlation of CO2 with temperature, and CO2 increases over time since around 7,000 years before present. Recent global warming and rising sea levels. Some misunderstanding exists on how global warming occurs and how it causes sea level increases. Recent warming over the last 10,000 years has been cyclical, a warming pulse followed by a cooling pulse. Sea levels rise in the warming cycle due to increased land ice melting and warm water volume increases. Sea levels lower on subsequent cooling as land water freezing occurs and cool water volume decreases. As already discussed, some 10 cycles are recorded in the most recent 10,000 years. Sea levels rise slowly over the warming 100 years by about 1 to 2 metres, then slowly lower again during the following 100-year cooling cycle. The two halves of this cycle roughly cancel each other out with no net sea level rise overall. This has happened about a dozen times in the last 10,000 years with little overall change in sea level during that period. The warming is not cumulative and the sea level change is also not cumulative. In the right-hand side of the chart below, we see the last 10,000 years of climate oscillations within the circle, oscillating by about 1 to 1.5 degrees centigrade. Lower down we have highlighted the last major temperature oscillation 10 to 12,000 years ago, which was from -8 degrees to about 0 degrees in one large temperature leap, corresponding to over 120 metres of sea level rise on that occasion. The chart below shows sea level changes globally over the last 20,000 years, including the major heating event about 18,000 years ago, discussed in the previous slide, at the end of the Pleistocene Ice Age, resulting in a sea level rise of about 120 metres and largely responsible for our present global coastlines. Since about 7,000 years ago, sea level changes have been minimal, up and down by 1 to 2 metres, even though there have been 7 warming/freezing events of 1 to 1.5 degrees. These sea level changes have cancelled each other out and should continue to do so if, as seems likely, similar temperature pulses such as we are currently experiencing continue to occur. There seems little concern for serious sea level fluctuations beyond some remedial coastal engineering work. The minimal total sea level changes of 1 to 2 metres over 7,000 years is listed at the top right of this chart. Most geologists believe we are still emerging from the last glacial advance. Warming is returning, is non-threatening, inevitable, predictable, unaffected by CO2, manageable, overwhelmingly beneficial, and cannot be prevented by any man-made intervention. As seen in the above climate chart, nature has been here before, at least 15 times in the last 2 million years. Nature has things well under control, and we could not be in better hands. The future of global warming. Global warming is occurring and will continue to occur until equilibrium is attained with the sun's energy output. This will occur when the Earth's global average temperature reaches 16 to 18 degrees centigrade. The Earth's average global temperature is currently around 15 degrees centigrade, after slipping several degrees during the very recent Pleistocene Ice Age, from which we are continuing to emerge, and hence why we are warming. This warming will initiate some not too serious sea level rises as the Earth's polar regions lose some ice cover. Ice as a feature of polar regions occurs over less than 20% of the Earth's history. Some low-lying islands and continental coastal fringes will be marginally inundated. Warming will, however, revitalise much of the world's agriculture, increasing significantly growing seasons and making regions above 40 degrees in latitude much more habitable and agriculturally and economically much more productive through positive climate changes. Any additional atmospheric CO2 generated through increased fossil fuel burning will also increase available CO2 for vegetation, currently being starved of this essential element for life at present levels. Low latitude regions will also warm, but more slowly with climate latitude shifts, but are much more adaptable, experiencing smaller changes than the higher latitude areas. There will inevitably be some collateral damage, with some winners and losers, but overall the Earth will be returning to more optimum conditions for life as we know it, and for which we are well adapted for. These natural warming and cooling episodes are not man-made. More than 50% of the world's potentially productive landmass experiences extreme, life-threatening cold for at least 6 months of the year. These areas are mostly at latitudes greater than 45 degrees. The other 50% benefits substantially from not experiencing any life-threatening climate, cold or hot at all, and supports most of the animal and vegetable life and agricultural activities on Earth. The bar chart in purple shows how the world's population is distributed in latitudes greatly favouring warmer conditions. Throughout Earth history, global cooling has proven to be an existential threat, and global warming a substantial life-affirming benefit. There is no climate problem or crisis. The geology of the Holocene, 12,000 years ago to the present, completely refutes the assertion of man-made climate change and the involvement of carbon dioxide as a climate trigger or driver. Carbon dioxide mitigation, carbon dioxide reduction, is unnecessary. Carbon dioxide is not a pollutant, but an already seriously depleted essential atmospheric gas. Carbon dioxide emissions from fossil fuel burning are a safe atmosphere-carried fertiliser delivered daily to every plant on Earth for free. Coal, with its contained carbon dioxide, is therefore already clean coal. There is no need for green or renewable energy technologies unless competitive with existing fossil fuel equivalents. There is no climate crisis. The climate is behaving with short interglacial warming episodes, normally and predictably, as it has numerous times during a great many interglacial warming cycles over the last few thousand years. There is no problem, and therefore no solution is necessary. Science cannot solve or model a non-existent problem. If carbon dioxide is not a climate driver, then no amount of computer modelling involving carbon dioxide will be able to recreate past, present or future climates or make meaningful climate predictions or projections. The best and cheapest climate option with the least impact on the economy, society and the environment is to do nothing. Carbon dioxide is not a problem. The cost of inaction is zero, and damage done to the economy, society and the environment would also be zero. Spending huge sums on massive climate and social engineering would ruin the economy for no actual climate benefit. If it ain't broke, don't fix it. For some classes and readers, this may be a convenient point to stop this presentation with a summary of some of the more important relationships on display. For those interested in progressing a bit further, there are a number of additional topics covered in the following dozen or so slides. Some further food for thought. All of the myriad of disaster and end-of-the-world scenarios that have ever existed have one thing in common. Not one of them has ever come true. Occam's razor. The most likely explanation is the one involving the least assumptions and complexities. Or more simply, the simplest explanation is more likely to be correct. This illustration shows how the basic scientific method works. It starts with an observation of some natural phenomena, about which we start to formulate a hypothesis of how that phenomena occurs. We then test the hypothesis via vigorous experimentation, and this may result in the need to modify the hypothesis to produce a new variant of the hypothesis, which then is again tested via more rigorous experiment. Eventually we get to the stage where the hypothesis seems to stand up to all tests, observations and experimentation,
and then we establish the hypothesis as a theory based on repeated validation of results. The climate model of climate science is based on carbon dioxide greenhouse warming theory and computer modelling and prediction. The climate model favoured by geology is based on billions of years of observation of climate and atmospheric history observed in the rock record. These two are contradictory and both cannot be right. Is the science settled? Claims that the science is settled, and 97% of the 2,500 IPCC scientists agree carbon dioxide causes climate change, are highly contested yet persist. There are very substantial counterclaims and protestations from a great many opposing scientists, equally qualified and familiar with the relevant science. The climate alarmist arguments, those believing in catastrophic man-made warming caused by carbon dioxide, often revolve around, if you are not a climate scientist, your opinion is worthless, unless of course you are Al Gore, David Attenborough, Greta Thunberg, or some other favoured personality or political activist. There are plenty of other eminent scientists, chemists, physicists, geologists, biologists, astronomers, engineers, and even climatologists who also have relevant expertise, but opposing opinions to bring to this topic. A concern is that not all relevant fields of science are being reported in this debate. Geology, which offers a completely different point of view based on a well understood continuous rock record of climate over billions of years, has been almost entirely ignored or isolated by media gatekeepers and the council culture brigade, determined to suppress the circulation of what they consider to be politically and socially unacceptable ideas.
Ocean acidification. The oceans act as an enormous carbon sink and have taken up about a third of the CO2 emitted by human activity. It has been estimated that the uptake of anthropogenic carbon since 1750 has led to the oceans becoming more acidic, with an average decrease in pH of 0.1 of a unit. No mention that coral reef formation as a major cause of ocean acidification, or that hundreds of millions of years when atmospheric CO2/acidification was much higher, it did not cause a problem. The pH of the oceans is around 8, mildly alkaline. The introduction of hydrogen ions in the above reactions causes the ocean pH to lower and become less alkaline. It does not become more acid, as the hydrogen ions immediately react with excess hydroxyl ions and neutralize. Only when the pH is lowered below 7 will the oceans become acid and have an excess of hydrogen ions. Introducing hydrogen ions at pH 8 will make the oceans less corrosive, less caustic, and increasingly more neutral until pH 7 is reached. Even under weakly alkaline conditions, some carbonate shells will begin to dissolve, as would happen in pure pH 7 water. This can be compensated for by the organisms producing more. Low CO2, however, also strongly adversely affects global vegetation, which is a much more serious impact on all life and seems to have been ignored in this debate. Ocean acidification by rainwater.
The use of the term ocean acidification is a misnomer until the pH drops below 7.0, which is unlikely in the present circumstances because there are enormous pH buffering reactions with geology, the rocks, countering the lowering of pH to anywhere near pH 7. Another contributor to lowering the ocean's pH is rainwater. Pure condensed water has a pH of 7, but rainwater has a pH between 5 and 6. Even compared to seawater, pure water is more acid and rainwater far more acid again. Every time fresh rainwater enters the oceans, it contributes substantially to so-called ocean acidification. We never hear of this being discussed, or the suggestion that rainfall mitigation, somehow decreasing rainfall, should be considered, or the fact that coral reef growth itself increases acidification. Is atmospheric carbon dioxide mitigation or removal possible? Atmospheric mitigation of carbon dioxide means the lowering or removal of carbon dioxide from the atmosphere by various means in order to artificially lower its overall concentration. The presence of carbon dioxide in the atmosphere is a function of two equilibrium reactions between atmospheric carbon dioxide and bicarbonate ions in water, and between bicarbonate ions and calcium carbonate, limestone, in the oceans. These two reactions are presented in the next slide. Equilibrium reactions do not go to completion, but shift in the direction that minimises any overall change and to largely and continuously replace any element that gets depleted. This means that any carbon dioxide removed will be largely replaced as the equilibrium reactions largely shift to replace any deficits. The consequence of this means that it will be virtually impossible to deplete atmospheric carbon dioxide to any significant extent until carbon dioxide producing reactions cease due to complete elimination or isolation of any of the major components capable of replacing that CO2, in this case bicarbonate ions and limestone. As this is never going to happen, carbon dioxide mitigation is a process doomed to failure. You cannot beat these powerful equilibrium reactions. You cannot defeat the inherent chemistry of these systems. Why this very basic high school chemistry level flaw in carbon dioxide mitigation schemes has not been recognised eludes me. Carbon neutral processes mean not increasing additional carbon dioxide into the atmosphere from human causes in order to keep atmospheric carbon dioxide levels at some predetermined level. The essential carbon dioxide carbonate chemical equilibrium reactions in water. The presently preferred climate greenhouse gas model for climate change favours atmospheric carbon dioxide as the main climate driver. The carbonate forming chemical reactions depend on the two equilibrium reactions involved. Reaction 1, carbon dioxide plus water, goes to form bicarbonate ion, a hydrogen ion or acid ion, occurring in the air-water interface in cold water high latitudes. The second reaction is bicarbonate ion reacting with dissolved calcium ion in the oceans to produce calcium carbonate, the mineral calcite and the rock type limestone. Calcium carbonate contains 44 weight% carbon dioxide. Also produced is another hydrogen ion or acid ion. The second reaction favours shallow warm waters in low latitudes.
The overall combined reaction is 3. Carbon dioxide plus water plus dissolved calcium ions going to produce calcite or limestone plus 2 hydrogen or acid ions. The equilibrium chemical reactions do not proceed to completion from reactants to products, but are in balance and proceed part way depending on the circumstances, particularly influenced by temperature and concentration. Removal of carbon dioxide from the system in reaction 1 drives equilibrium reactions 1, 2 and 3 to the left according to Le Chatelier's principle. When stress is applied to a system at equilibrium, the system will adjust to minimise the stress. If carbon dioxide is removed from the atmosphere, reaction 1 progresses to the left to replace that carbon dioxide. This depletes the bicarbonate ion in the system in reactions 1 and 2, causing reaction 2 to progress to the left to replace the lost bicarbonate ion by dissolving some limestone. Ocean acidification. These reactions produce limestone, including coral limestone, which would not exist without abundant carbon dioxide. These reactions also produce significant acid hydrogen ions. Coral reefs are themselves important contributors to ocean acidification. The oceans have a pH of 8.1, which is mildly alkaline. Rainwater, pH 5, and mildly acid, also surprisingly contributes to ocean acidification. Equilibrium chemical reactions and Le Chatelier's principle. To repeat, Le Chatelier's principle states that when stress is applied to a system at equilibrium, the equilibrium shifts in the direction that minimises the applied stress for the following reasons. In this table, stress is the applied change to the system. The shift is the way the equilibrium adjusts to minimise that stress, and Y explains the reason for the change. For example, the stress might be to increase the concentration of a substance. The shift will be away from that substance in the chemical reaction, and the reason is the extra concentration of that substance needs to be used up. The converse might be a decrease in concentration of a substance as the stress. The shift will be towards that substance that's being decreased. And the reason is the need to produce more of the substance to make up for that which was removed. The other stresses illustrated in this table can be followed through by yourselves. Correlation and causation in the CO2, carbon dioxide, versus temperature debate. In the geological climate record, temperature is seen to increase, correlate, with CO2. Because temperature changes are nearly always associated with CO2 change, CO2 was mistakenly believed to be the driver for temperature. However, it was later recognised that increasing temperature increases CO2 because it reduces the solubility of CO2 in water. It is the temperature which causes or drives the change in CO2, not the reverse. For the first time in the modern era, see next slide, an increase in man-made industrial carbon dioxide occurred unaccompanied by any temperature increase. The carbon dioxide rose from 260 to 415 parts per million, an increase of almost 150 parts per million, but so far there has not been any concomitant rise in temperature to match previous equivalent temperature rises accompanying earlier similar CO2 rises in the past. If CO2 is the climate driver, this should never happen. The temperature now should be some 15 degrees Fahrenheit, about 8 degrees centigrade, warmer to match temperature or temperatures presumed caused in previous similar magnitude fluctuations in carbon dioxide. That this has clearly not happened provides proof that carbon dioxide does not drive temperature or climate. These relationships are explained more fully in the diagram in the next slide. A present-day example of carbon dioxide increasing without any sign of associated warming. Why is there no equivalent increase in temperature to match the dramatic increase in carbon dioxide in this diagram at the right-hand margin? Is this because man-made carbon dioxide occurs first and is unrelated to existing temperature and is not a climate driver? That man-made industrial carbon dioxide increases in very recent times, as registered on the extreme right of the chart in blue, have not been matched by temperature increases of 10 to 12 degrees to match the equivalent magnitude carbon dioxide increases seen elsewhere in the chart, strongly suggests that carbon dioxide is not a climate driver. More advanced level topics. Greenhouse gases and the carbon dioxide debate. This discussion and analysis particularly relates to how greenhouse gases absorb heat from outgoing radiation. This is most simply explained in the chart below. Greenhouse gases in the atmosphere intercept and absorb thermal radiation at particular frequencies or wavelengths, being reflected back into space from the Earth. Without any atmospheric gases, the blue line represents the reflected energy. The black curve above represents the energy reflected in various wavelengths for the existing atmosphere, with its existing 400 parts per million carbon dioxide. The green curve represents reflected energy with no atmospheric carbon dioxide. The red curve with 800 parts per million carbon dioxide is double the existing carbon dioxide level. The difference between the black and blue curves is the absorption, largely by water. Between the black and the green and red curves, the absorption of the respective amounts of carbon dioxide. Doubling the carbon dioxide from 400 to 800 parts per million makes negligible difference to heat absorption and hence increased temperature. The detailed chemistry behind this is well explained in the video link at the following website. The important point to note is that as atmospheric carbon dioxide increases, the additional absorbed heat that is retained rapidly decreases. See the chart in slide 15. Getting to the point that even doubling from 400 to 800 ppm will have minimal heating impact. Additional atmospheric carbon dioxide at present levels of around 400 ppm will have minimal temperature or climate impact and should not be a concern. At these present carbon dioxide levels, even substantial carbon dioxide mitigation at enormous cost will have minimal cooling impact and may not be worth even contemplating. These complex atmospheric relationships are little known and understood and are still widely debated by atmospheric physicists. Only one of these scientists is working in the real world that actually exists, looking at real, verifiable, hard rock, factual information on climate going back billions of years and generating real climate data and predictions. Why has the enormous contribution that the science of geology could contribute to the science debate been ignored? The hard evidence against climate alarmism is there, preserved in the rock record, to be seen and understood by everyone.